Math 242, Cuesta College. I'm Joe Vasta. We are going to cover some lecture here over inverse functions. I keep checking to make sure the lighting is good. Looks pretty good. Maybe I'll do that a little. We'll put some blinds up. Okay, so here it goes. Well, we are going to look at inverse functions. The homework is bookwork and a handout. The handout is on the website. So these guys right here are functions, collection of ordered pairs, inputs and outputs, and they want us to find the inverse. Okay, the inverse of f equals, it's gotten by switching the input and output pairs. So where 1 is the input and 4 is the output, the inverse says 4 is the input and 1 is the output. So you just switch those coordinates. The next one would be 6, 2, 5, 3, and 5, 4. That right there is the inverse of function f. Now, the deal about the inverse of a function is the inverse might not be a function. So we had a function here, and you can tell it's a function because the first coordinates are all different. This one right here, if you look at the first coordinates, you got that and that, which means the inverse is not a function. So that is the deal. I think in this class we did arrow diagrams. If you want the arrow diagram for the original function f, 2, 3, 4, should be using black ink here. And we have 4, 5, 6. 1 goes to 4, 2 goes to 6, 3 goes to 5, 4 goes to 5. So that is a function. This is f, because every input has exactly one output. Those arrows there are a little messy. Now the inverse takes the arrows and switches them the other way. So I'll go ahead and draw a diagram. 4 goes to 1, 5 goes to 2 places, 3 and 4, and 6 goes to 2. So there is an input right there, 5 I guess, that has 2 outputs. Okay, let's go ahead and find the inverse of g. Okay, it's pretty simple to do. All you do is switch the coordinates. 5 goes to 1, 6 goes to 2, 4 goes to 3, 7 goes to 4. There's the answer. Now, is the inverse of g a function? Well, let's look at the first coordinates, 5, 6, 4, 7. We don't have any repeats, so this guy is a function. Okay, if they asked for the domain of g, it is 1, 2, 3, 4. that domain of G becomes the range of the inverse. See, the range is 1, 2, 3, 4. And the range of G, which was 5, 6, 4, 7, or 4, 5, 6, 7, becomes the domain of the inverse, 4, 5, 6, 7. So what the inverse is an undoing machine. It switches the inputs and the outputs. It switches the x's and the y's. It switches the domains and the ranges. So it's a good thing, lots of times, when you have a function, for the inverse to also be a function, like in problem 2. In problem 1, it's not that case. The inverse was not a function. So when the inverse is a function, it has notation. Well, we can't just call it G. We're going to call this G inverse. So there is a symbol for the inverse, and it's confusing if you've never seen it. It looks like an exponent, -1. So we just call this G inverse. This notation right here does not mean go 1 over G. So we don't want to write that. This is just notation. It may have been better if they had used a star or something else, but they used what they used. So when a function has an inverse that's a function, so when a function has an inverse function, then that function is called 1-to-1. So let's write some of this down. A function is a relation, correspondence between inputs and outputs, where each input has one output. A 1-to-1 function is the condition where it's not only a function, but each output has one input. And so we could have looked at G and known right off the bat that its inverse was going to be a function by looking at the outputs and seeing that they were all different. Where we go back to F, we looked at the outputs. Well, we didn't do that, but if you look at the outputs, you see a repeat in these outputs. So you know, even though it is a function, function F here is not 1-to-1. So we'll write this down. F is not. Now, we don't always want to write 1-to-1, so we're going to use this notation right here. So 1, a dash, and a 1. F is not 1-to-1. G is 1-to-1. And so that's what we have here. So let's go ahead and get a blank piece of paper. So we have relations, and we learned that in chapter 1. Checking to see if it's blurry or not. I think it's good enough. And there are relations that are functions. That's where every input has one output. And then there are functions that are 1-to-1. So we're going to do some equivalent statements. First one being G is 1-to-1. the second statement would be that G has an inverse function called G inverse. And the third statement we're going to make, we'll come back to this, so I'll put this sheet back up. Okay, let's take a look at F and G again. So remember that F was not one-to-one, and G is. So what I've done with F, it's a set of ordered pairs, 4 ordered pairs, input, output, etc. And you can graph those as points, and so that's what I did. There's 1, 4, 2, 6, 3, 5, and 4, 5. And then I went ahead and did the same thing with function G. So those are functions because they pass the vertical line test. The vertical line does not hit the graph more than one time. So there's my vertical line. I should probably get that out of there. So that tells you that every input has one output. Now the thing that concerned us with this one right here were those 5s there, which is right here. 5's an output or a Y value. And there's actually 2 inputs. The inputs are on the x-axis that go to the height of 5 or go to the Y value of 5. So we can tell if a picture is going to be one-to-one or if a function is going to be one-to-one by seeing if it passes something called the horizontal line test. And the horizontal line test works like the vertical line test. So the vertical line test tells you if a picture is a function, and the horizontal line test tells you if a function is one-to-one. So this one fails the horizontal line test. Okay. Now, we could have taken the other approach where we could have graphed the inverse of F. So here's the inverse of F. And the inverse of F looks like this. 4, 1, and I'll do this in blue. Hopefully it shows up and you can see the contrast. 6, 2, 5, 3, and 5, 4. And so you can see that these 4 points that I graphed right now, they don't pass the vertical line test. That says that the inverse is not a function. Okay, so those 4 points are not a function. Okay, this graph over here, it passes the vertical line test, which makes it a function. It also passes the horizontal line test. So the horizontal line test says the horizontal line only hits the graph one time, does not hit it more than one time. So this one passes the horizontal line test. Now, we could graph the inverse of that. So here's problem 2. Here's the inverse. And I could just switch the coordinates. So 5, 1, 6, 2, 4, 3, and 7, 4. And that's what the inverse graph looks like. Okay, notice the inverse graph happens to be, maybe I should highlight these guys in green. They might be hard to see. There's the inverse. The inverse indeed is a function. We called it G inverse. But look what we see here. When you graph a graph in its inverse, I'm going to go draw the line if I can draw it here. Y equals x. And you see that the inverse, here's your original graph right here, G. The inverse is a reflection through that line, y equals x. And so that's something important to know. We could have done the same thing over here. We could have said, oh, here's the inverse right here. I'll do this one without a ruler and see how good I get this here. Yeah, I guess the ruler is better. Oh well, it's good enough for government work. Even though the inverse was not a function in this example, it's still a reflection through that line, y equals x. So what we have here is the next condition for this. G is 1 to 1. That means G has an inverse function. We'll call it G inverse. And G passes the horizontal line test, which is like the vertical line test, but with the horizontal line. Okay, so we're going to do some examples. These are the examples you'll see on the handout. Remember, we said the homework is some book work and some handout. So there are 3 graphs, and we're supposed to classify all 3 as one of the following: not a function, function not 1 to 1, or a 1 to 1 function. So if we go back to this Venn diagram here, and that's what it was, I didn't mention that, is that these graphs live in one of these regions. And there's 3 regions. This outside region is not a function. This middle region here is a function, but it's not 1 to 1. And then this third condition is a 1 to 1 function. Okay, so let's go ahead and see what we're going to do. And it's actually not that bad of a thing. To see if something is a function, we've already done this earlier in this class. It has to pass the vertical line test. This passes the vertical line test. Does this function is made up of 2 line segments? Does it pass the horizontal line test? Does a horizontal line hit that picture more than one time? And the answer is no. So this passes both tests, which makes this one 1 to 1, which is the third condition. These are labeled 1, 2, 3, and I know the problems are 1, 2, 3 as well, so hopefully that's not too confusing, but it could be. This is a 1 to 1 function. Let's go ahead and analyze the other pictures, and then we'll go back to all 3 of them and graph the inverse. So this guy right here, this picture on problem 2, we have to ask ourselves, does it pass the vertical line test? We always start off with that one. We see if it's a function. Well, the vertical line right where my pen is hits that graph twice. So it does not pass the vertical line test, which means this is not a function. So this is the first one, not a function. Okay, the third graph looks like a parabola. We can see it passes the vertical line test, so it is a function, but does it pass the horizontal line test? Here's a horizontal line that hits it in 2 spots, so it does not. So this problem here is a function, but not 1 to 1. Okay, the second part says graph the inverse. So how would we graph the inverse on this? I would actually take some key points, like this point right here is, what is it? It's 4, 0. That one's going to get graphed to 0, 4. You know what I'm going to do? I'm going to make the inverse be in red. Let's see if we can see that. Yeah, I'll do it in red instead of blue. So 4, 0 is on the original graph. 0, 4 will be on the inverse. 0, 4 is right here. Okay. So we also have another key point on this graph, which is this guy right here. This guy is 0, 2. So the inverse is not going to have 0, 2. The inverse is going to have 2, 0. And then we have our last key point right here, which is -1, 3. And on the inverse graph, that's going to be 3, -1. So we'll put a dot right there. You don't have to label all the points. The important thing is the inverse graph is going to look like the same creature as the original graph. The original graph is 2 line segments connected together, so the inverse graph is going to do the same thing. It's going to look like that and like that. And as you can see, you don't have to do this, but those 2 graphs, and I didn't do it perfectly, they are reflection through the line y equals x. You don't really have to draw that line y equals x when they ask you to graph the inverse, but when we draw it, we can see, everything that was on the black graph gets reflected over that line, and then on this side it gets reflected the other way. Let's go ahead and do this one right here. So even though it's not a function, it's still going to have an inverse. And so what we want to do is maybe take this point 2, 3 and graph the corresponding point on the inverse graph, which would be 3, 2. So really what I'm doing is I am reflecting that point through the line y equals x, but if that hurts your brain, just go ahead and switch the coordinates. I'm going to take the point down here, which is 2. I didn't put scalings on these axes, did I? Shame on me. Oh well. 2, -3. And then the corresponding point is going to be -3, 2. Okay, everything's under control here, but wow, that was a close one. And then we have these 2 points. I mean, this one right here is 1, 0, and this one right here is 3, 0. And those are going to get graphed to 0, 1 and 0, 3. And so this creature right here, we never said what it was called. It's an ellipse. We'll study this later in this class. And so its inverse is also going to be an ellipse. An ellipse is like a smushed circle. And there it is. And we can draw this line right here. We're done with the problem right here. But I'm going to draw this line right here just for the extra motivated student. They can see that that is a mirror reflection. The last one is our parabola. It has the point, I'm not going to label all the points. Let's see if we can do this without labeling all the points. 0, 0 is going to go to 0, 0 for the inverse. You just switch the coordinates, and 1, 1 is going to go where? 1, 1. 2, 4 is going to go to 4, 2. 1, 2, 3. Ah, this is good planning on my part. Negative 1, 1 goes to 1, negative 1. And negative 2, 4 goes to 4, negative 2. So the inverse of a parabola is a parabola. And so that is what you have to do in your homework. I won't put the green line there, but you could imagine, you can see the reflection. Okay, we'll continue on here. And how are we doing in terms of blurriness? We're doing good enough. Okay, so in your homework, they're going to give you a one-to-one function, and all you have to do is find the inverse function. They may say, verify something algebraically. We don't need to do that. Okay, so remember that the inverse function is gotten by switching inputs and outputs, domain and range, everything switches. So if they give you a function like this and they ask you to find the inverse, here's 4 steps that will always work. Replace f of x with y, switch x and y, solve for y, which could be the hardest step in some cases, replace y with f inverse. Okay, so step 1, replace f of x with y. Okay, now step 2, switch x and y. When you do that, you actually get a different graph. So I'll do this in blue. We have x equals 2y minus 2. And now we're going to solve for y. So I add 2 to both sides. And I divide by 2. And so I have x plus 2 over 2 equals y. We can write it as y equals x plus 2 over 2. Now some of you would want to write this as 1/2 x plus 1 by splitting the fraction, but you don't need to do that. You do see that this is a line and so is the original graph. Any one of these are good enough. Okay, our last step, replace y with f inverse. So that's what I'll do. I'll just use the first one. F inverse x equals x plus 2 over 2. And so let's see what this looks like. Suppose you're doing some cryptography and you want to use this to encode something. So you might take this message. So we're done with the problem. Hello world, or whatever, and start assigning these to numbers. So H. So A, B, C, D, E, F, G, H. That's an 8. And then E. A, B, C, D, E. That's a 5. Okay, and so on. So you want to encrypt this message. You start off by doing it one letter at a time. You put 8 into that function, and you end up getting 16 minus 2, which is 14. Now, as this thing's traveling along, it gets to the other person, your ally across the ocean, and they have the inverse machine, the undoing machine, the decryption. And when they put 14 into here, look what we have. 14 plus 2, 16, 16 divided by 2 is 8. And so people in the world of cryptography will use inverse functions for that application to encrypt, decrypt. Now, of course, they don't do this anymore. I mean, everything's ASCII base 2. It's a lot more complicated than this, but they still use inverse functions. And so you can just take any number, put it in there, put it in the inverse, and it gives you the same number. So what some teachers and books say is that, well, this is a composition. This is f inverse composed with f of x. Now, it looks like I wrote them in the wrong order, but remember the inside function, that's the first function composed with the second function. And what a lot of books will say is, here's the algebraic property of inverses, where that gives you the same value. You can also do it the other way, where you have f of f inverse of any number gives you that very same number, which means if I took these factories and big hands came out of the sky and switched them, you would have the same result, where if you put a 15 in there, you would end up getting a 15. Okay, so I probably told you more about inverses than you wanted to know. Let's go ahead and do the next problem. We're almost done with this section, so we only have 2 more problems to do, and then we march toward logarithms. Okay, it says find the inverse. And what I'll do is I'll fold this paper up here. Hopefully this doesn't leave the focus is all right on there. Yep. And those are my steps. Find the inverse. How do I find the inverse? I replace f of x with y. I switch x and y around. That means everywhere there's an x, I put a y, and everywhere there's a y, I put an x, and then I solve for y. So I'm going to multiply this equation by a y plus 2 on both sides. So I have y plus 2 times x equals, the y plus 2's on the right-hand side will cancel, and you'll have y minus 2. My next step is to solve for y. I'm going to distribute the x. Okay, so now I have a y term there and a y term there. I want to put them on the same side of the equation. Now, it doesn't really matter which side you put them on. I'm going to go ahead and put them on the right-hand side. So I'll have y minus xy by subtracting that on both sides. And I'll also add 2 to both sides of the equation and get 2x plus 2. Okay, the reason we do that is so we can factor out a y so we can solve for it. 1 minus x. So I have solved for y there, almost. Okay, I'll move these rules because I need more space. So let's just rewrite this. Y times 1 minus x equals 2x plus 2. I'll divide both sides by the 1 minus x. And so that gets y all by itself. You don't need those parentheses on the bottom. Now, some people would say, well, can I factor out a 2? And the answer is yes. but it's not going to help us, reduce the fraction. So that you don't really need to do that. This is good enough. So let's write our answer officially. That y is f inverse, that's step 4, replace y with f inverse. And then we have 2x plus 2 all over 1 minus x. And there's your decryption machine right there. There's your inverse function. So let's go ahead and do the last problem that we'll cover from 5.2. And it's this one right here. Find the inverse of this, which has a cube root in it. Okay, so I'm going to replace f of x with y. Step 2, switch x and y. Step 3, solve for y. Now this is a little scary. We want to solve for this thing right here. So I'll add 5 to both sides. Now this is just a matter of preference, and I wanted to do it on the other equation earlier. I'm going to just switch sides and put the thing I'm solving for on the left-hand side. Okay, my next step is I'm going to cube both sides. The reason I cube both sides is because the cube will kill off that cube root. Okay, it will write 3 copies of this, and when you have 3 copies of a cube root, it just becomes the 1 power. You could also say the cube root is the 1/3 power, and so you have 1/3 times 3, which gives you 1. In any case, you get y plus 1 equals x plus 5 cubed. My last step is subtracting 1 on both sides. Well, it seems like my last step. There's one more thing I'll have to do. And we have that right there. Now, some of you might say, should we multiply that out? But we don't have to. This is good enough like this. We do have to change the y to an f inverse x. And so that's all I'm doing right here. Okay. Now, there are problems in your homework that have square roots, and they get a little more complicated because we are limited on time this semester due to certain events in the world. I'm going to go ahead and say when you're doing your book work for 5.2 that you should skip 5 through 8 and 11 through 14. If you remember to do that, you'll be all right. So, you guys do your homework, and the next lecture should be logarithms.